SDN is changing the way career networks are designed by enabling innovation and differentiation in networking. In this video, we will take a look at different aspects of career SDN. Carriers or service providers need to bring down operating cost and monetize their networks through quick services to end customers. In order to meet business demand, networks need to dynamically provision bandwidth for their customers. Normally, provisioning and configuring networks are manually intensive processes focused on individual vendor-specific network elements. These manual configurations cannot keep up with rapidly changing devices and networks, creating outage risks for network, compromising revenue, customer trust, and delay the introduction of new services. Carriers need simplified network operation, quick provisioning, and end-to-end visibility in the network. SDN solves this problem by introducing centralized control, programmability, and flexibility into the network operation. It is not a single technology, but rather an interplay of multiple technologies that enables SDN in carrier networks. The most popular technology choices include Path Computation Element Protocol or PCEP for centralized provisioning of network path, Link State BGP for topology discovery, segment routing for simplified forwarding plane, and netconf YANG for centralized configuration of services at large scale. Let us discuss a few important use cases for carrier network and the corresponding enabling technologies in the next few slides. The most important application of SDN into carrier networks is end-to-end path optimization and provisioning. Carriers need ability to respond to dynamic bandwidth demand in real time using the power of abstraction. These dynamic demands can be driven by scheduled increase in bandwidth by the controller during peak usage hours to facilitate heavy activities like data center backup. Secondly, increase or decrease of LSP bandwidth for optimization of resource usage by the controller. Last but not the least, networks need to handle ingress-initiated bandwidth provisioning to handle dynamic increase in data traffic. SDN makes these possible through programmable network and centralized end-to-end view. The enabling technologies can be categorized based on their functions. The controller does topology discovery to learn about the link state information of the network. This is achieved by BGP-LS. The controller communicates to the network infrastructure through a southbound protocol. Based on request from the ingress, the SDN controller computes the appropriate path and assigns it to ingress through Path Computational Element Protocol PCEP. And finally, the network infrastructure overlay is based on either traditional RSVP-TE or segment routing. ISIS or OSPF or BGP segment routing distributes labels along with IGP routes and uses MPLS forwarding plane to provide end-to-end connectivity. To achieve dynamic provisioning in this type of network, the PCE controller can be programmed to trigger the PCC to initiate make before break for RSVP-TE LSPs. A PCC can request the controller to assign a new LSP with higher bandwidth based on its incoming traffic situation. In a segment-routed network, the PCC controller learns the complete view of the network, including the TE states, through BGP-LS. The controller calculates a higher bandwidth path and informs the PCC about the LSP. In the next section, we will understand the validation needs of all pieces of technologies to ensure end-to-end functionality of the use case. The SDN controller plays an important role behind end-to-end path optimization and provisioning. The controller calculates optimized path and communicates with the network infrastructure elements through PCEP. Ensuring the functionality and scale for the PCE is critical for success. Important aspects to be validated includes PCE's capability of synchronizing existing LSPs and controlling LSPs delegated to the controller. Second, PCE's capability of calculating optimized path based on existing network state and traffic engineering constraints. Third, PCE's capability of initiating, responding, and controlling LSPs. Fourth, ability to do dynamic provisioning upon topology change or network failure. Fifth, scale and performance of the PCE in handling large number of PCCs and large number of LSPs. And last but not the least, PCE's capability of handling segment routing or RSVPTE LSPs should be validated. To validate these, network engineers need the help of a tool which supports end-to-end validation with comprehensive coverage. Ix Network supports a powerful PCEP validation solution for ensuring these aspects of a PCE controller. Please watch our product demo videos to learn more about Ix Network PCEP solution.